Hello, I'm Kimberly Chan, and I'm a graduate student in Professor Ali Mesbah's research group at the University of California, Berkeley. Today, I'll be presenting our work done in collaboration with Professor Joel Paulson at The Ohio State University on deep learning based nonlinear model predictive control with offset free tracking for embedded applications. Model predictive control, or MPC, is a well known method of control that involves the repeated computation of an optimal set of control inputs to reach an objective in a receding horizon fashion. And advantages of MPC include its ability to use the system model and account for constraints, its ability to handle general control objectives, and its ability to incorporate system uncertainties. Some disadvantages are that MPC can generally be computationally demanding and that stability and feasibility are not generally guaranteed. Despite those disadvantages, it has gained popularity in several emerging applications, including autonomous vehicles, biomedical applications such as plasma jet treatments, and humanoid robots. Qualities of these emerging applications may include the fact that they're large scale, highly nonlinear, have fast dynamics, and/or are safety critical. At the same time, many of these applications require some sort of embedded system in an effort towards automation. And challenges of embedding MPC for these emerging applications include the need for real time computation, resource limitations in the hardware, and challenges of numerical robustness at low computational accuracy. Thus, the goal of this work is to demonstrate an embedded control system that results in fast operation with offset elimination towards automated control. A subclass of MPC problems is the tracking problem. So nominally, MPC is designed to control a given system and reach a target steady state, and a general formulation is presented on the right. But what happens if we change the objective? The issue of feasibility arises, and as a result, the failure to track these new objectives. So then the solution is to reformulate the optimization problem in MPC. And a well established or known method involves defining a parameter vector theta that contains the steady state's inputs and outputs. And then the cost function is modified with this parameter vector and the target reference R. So then finally, this optimization problem can be reformulated based on this new cost function. And at the end of this, we can define a control law based on the optimal input, just as we would for the nominal case. However, computation of this optimization problem can still be pretty expensive, especially for nonlinear systems. So how can we embed a computationally challenging problem such as MPC for tracking? First, some desirable properties we want for the embedded sense includes low computational complexity for fast and simple computations, and a small memory or resource utilization. So first, explicit MPC has been proposed as one solution, but it does not. It can't be used for nonlinear models and cost functions. So instead, approximate MPC using deep learning has been proposed as a promising alternative. So for this study, for the hardware device, we explore the use of field programmable gate arrays, or FPGAs, which are integrated circuits or chips that are composed of configurable logic blocks that are linked and reprogrammable. They are resource limited hardware with limited power, memory, and computational resources, and as such, they cannot handle predictive control algorithms at fast sampling rates and ensure constraint satisfaction. So in particular for this work, again, we approximate MPC using deep neural networks. So given some implicit MPC control law, we can approximate it with some explicit control law. Again, here we use DNNs, which have been shown to efficiently represent these non-smooth control laws that arise from various nonlinear MPC problems. Once trained, the DNN approximation can replace this online solution of the implicit MPC problem. And DNNs are chosen because they have, at least for the embedded sense, these desirable properties. First, they're cheap to evaluate, and then second, they have a low memory footprint. But a problem arises when using this approximate method. There is an induced error from approximating the MPC law, and thus we are no longer offset free. So in order to combat this induced error, we introduced a correction factor. So here we have our control law, and then in red we've introduced our steady state tracker, which is a correction factor. So given our parameter vector theta of steady states inputs and outputs, the target tracker is posed as another optimization problem. In this optimization, LS is the steady state cost function, which is assumed to guarantee this optimization problem has a unique solution. We present theorem 1, which assumes the constrained set of states and inputs contains at least one feasible steady state, and then the offset cost VO satisfies the properties of an exact penalty function. Then this offset-free DNN-based MPC law exists for any reference and guarantees that a closed-loop equilibrium exists such that the reference is the output of that equilibrium point. So then it should be noted that theorem 1 demonstrates an offset-free equilibrium point exists, but it does not guarantee that the controller converges to this equilibrium. So in practice, some stability analysis and/or performance validation should be performed. Some additional properties of this correction term are sort of discussed here. So when the approximation error equals 0, the correction term approaches 0. And so in fact, the offset-free MPC law is exactly the DNN approximated MPC law, and then both are exactly the implicit MPC law. And because of this, we can observe that the correction term corrects for the bias around the equilibrium condition. In other words, as the approximation error approaches 0, the closed loop system becomes more attracted to the equilibrium manifold, and then as a consequence, these fairly small approximation errors can be overcome as no other equilibrium with the same steady state input exists. What's important to keep in mind for our embedded system is that the steady state tracker has some desirable properties. It is both small scale and static. So then before I go into our case study, I'd like to quickly discuss the FPGA implementation. Implementation of this control law on an FPGA device requires the translation to or generation of hardware-level code. Here we use a high-level synthesis workflow, or HLS. HLS is a method to automatically convert a high-level description, such as MATLAB M code or C code, to hardware-level code. And then afterwards, we can deploy or program the hardware device using hardware-level code, using the hardware-level code generated, and then perform hardware or FPGA in the loop simulations. So recall that we are working with resource-limited hardware, and so that means several design considerations or so-called tuning knobs at each step of the design process affect the feasibility of the final implementation. So for example, the size or complexity of the control algorithm determines if it can be deployed on the final device, given the finite number of resources. So for our case study, we look at the benchmark case study presented in Morari and Mater, which is a simple bilinear system with plant model mismatch. The plant model is presented on the right. It's a single input, single output system with controlled output X1. The control objective is to, of course, track multiple reference values over time. For embedding the control algorithm, we use the programmable logic side of a Zybo Z7 development board by Digilent. And then something to note in regards to embedding the control law. First, it requires embedding both the DNN and the tracker, which is, remember, the target tracker is an optimization problem. And so while the target tracker could be amenable to these embedded systems, it may involve a sort of non-trivial workflow. So for simplicity, we approximate the target tracker with a second DNN. So in this case, we have one DNN to approximate the control law, and then a second DNN to approximate the target tracker, and both are embedded in this FPGA device. So with this given case study, we performed closed-loop simulations with the proposed control law. First, we address the need to optimally choose hyperparameters for each DNN that we embed. In order to find the best combination of hyperparameters for each DNN, we choose to approximate the target tracker first. Its accuracy can sort of compensate for larger errors in the explicit DNN approximation of the MPC law. So then we utilize the remaining resources to find a particular combination of hyperparameters for the DNN approximation of the MPC law. So on the right, we have this heat map that sort of demonstrates the search. we chose the combination of hyperparameters that was both feasible and gave the lowest mean squared error. In this case, it was 2 hidden layers and 6 nodes. So then in our closed loop simulations, we showed that the offset eliminating tracking can be achieved. Here, if we compare the blue line, which is the offset-free formulation we proposed, with the exact solution in green, we can see that they're quite similar, and in fact, the proposed solution does eliminate the offset. And in addition, the DNN approximation without the correction shown in red demonstrates some level of offset for which the the blue line is able to compensate for. And finally, hardware in the loop simulation show that the combination of both DNN approximations of the target tracker and the MPC law is able to track. And this is noted or shown in the dotted magenta. So in conclusion, we proposed a novel correction factor to eliminate offset for a DNN-based tracking MPC, and we demonstrated that an embedded version of this modified control law on an FPGA device. So for future work, we hope to develop a systematic framework for embedding these deep learning-based MPC algorithms on resource-limited devices. We'd like to explore emerging system-on-chip architectures, which may involve multiple onboard components, each of which can be optimized for specific computations of these control algorithms. And then we could investigate robust control formulations to explicitly account for uncertainty. And finally, we could incorporate guaranteed constraint satisfaction techniques, such as projection-based strategies for safety-critical applications.